Hello guys, welcome back to the MACM 101 Discrete Mathematics Tutorial 5. Last week, we learned the sets and operations on sets. So we created a collection of practical questions about sets and operations. In this tutorial, I will provide you a detailed solution for every single question. Let's move on to question 1.
Here is the question 1. We have a set A which has 3 elements. We have element 1 and a set that has 1 as an element and a set that has 2 as an element. And the question asks you which of the following statements are true. Let's have a look at the statement A. The statement A says 1 belongs to A. So by definition, we have if A belongs to element A belongs to A, which means A is an element of A. And if A not belongs to A, so A is not an element of A. So what do we have in the set A? We have the element 1, right? So A is the element of set A, which means, 1 is the element of set A, so which means 1 belongs to A. So the first statement is true. And the statement B, it says the set which has 1 as element belongs to A. So we have the set which has 1 as an element in the set A. So this set here belongs to set A. So this statement is true as well. In statement C, the statement C states that the set which has 1 as an element is a subset of A. So what's the subset? By definition, so B is subset of A if every element of B is also an element of A. So which means B is subset of A if and only if for all x belongs to B implies x belongs to A. Right. So here we know 1 is part of, so here this one is set B and here is set A, and 1 is part of set B, and 1 is part of set A. So B is a subset of A. So the statement is true. For the statement D, it says the set which has an element set 1. So this set is set B, and we have a set has its element, and the inner set has an element 1. It says the set B is a subset of A. And by definition, so we check if this set belongs to B. Yeah, this set belongs to B, right? And does this set belongs to set A? We have here this set is also it also belongs to set A. So this element belongs to both B and A, which means B is a subset of A, right? So we have this statement is true. And the statement E, it says this set, the set which has 2 as an element belongs to A. Do we have the element in set A? Yes, we do. We have this set here. So this set, the set which has element 2, belongs to set A. So this statement is true. And for statement F, we have this set is, so the statement states that the set which has 2 as element is a subset of A. So we have checked the set B. So we have checked the element in set B. We have checked if the element in set B is an element in set A. So we have 2 as element, and 2 belongs to the set of 2, right? But we don't have the element 2 inside of the set A, which means this set, which means the set B here is not a subset of A. So this statement is false. In statement G, it says the set B is a subset of set A. So in set B, we have an element set which has element 2. So do we have this set? Do we have this set inside of set A? We do, right? So because we have the set here, so the set B is a subset of set A by definition. So the last statement is true. So we have true, 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 false, true. Yep. This is question 1. It's very simple and easy. Yep. Let's move on to the question 2. In this question, I will not write down my solution step by step because it's hard to draw a perfect Venn diagram. So I will help you go through my interpretation and show you the meaning of Venn diagram for each operation. So let's have a look at the operation A. It asks you to union the set A and B, then do the intersection with C. So what do we have here? We have set A is 1, 2, 3, 4, 5, and set B is 1, 2, 8, 4. So after union, we have a union set that 1, 2, 3, 4, 5, 8. And after that, we intersect the union side with set C. We have 1, 2, 3, 5, 7 in set C. Then if the set C intersect with the union set, we got 1, 2, 3, 5, because the 1, 2, 3, 5 is the only common part of both the union set and set C. Here is the Venn diagram. So when you draw a Venn diagram, you don't simply draw 3 random circles and label that. You have to consider the element in set. So for example, in set A, we have element 1, 2, 3, 4, 5. And suppose that we have a set E has element 1, 2, then the diagram should look like this. The outer is A and inner is E, because E is the subset of A. If you want to draw 2 circles that like this, then the intersection will be 1, 2, and if this is A, this is E, you have to label that nothing here. Right, okay. So here is the Venn diagram for operation A. We have it asks you what A union B. So A union B should be this one. So we have something here and intersect with C. So here is C. So A union B intersect C actually is this part. If you want to draw the diagram normally, we have to draw 3 circles. And well, we have 1, 2, 3, 4, 5 in A, and 1, 2, 4, 8 in B. So the common part will be 1, 2, 4, right? And this part will have 8, and this part, this part will have 3, 5. But 3 and 5 is also an element in set C. So 3 and 5 should be here, and nothing should be in this area. And we don't have the element 8 in set C, so nothing should here. So 8 should be in this part. So in this part. So if you want to draw a Venn diagram like this, you have to label the element in each part. Otherwise, it will be ambiguous. Right? So let's move on to the second one. So second operation is A union B intersect C. We have to do the intersection first. So we have B is 1, 2, 4, 8, and C is 1, 2, 3, 5, 7. So intersect B and C, we got 1, 2. Yeah, we got 1 and 2. Only 1 and 2, because this is a common part of both the set B and C. After that, we do the union. So we do 1, 2, 3, 4, 5 union 1, 2 is 1, 2, 3, 4, 5. So actually it's just set A. So what we have here, so this part, yeah, in order to show that clearly, we cover the B intersect C first. So this is the B intersect C, and here is the set A as well, and its result as well, because the final result is just the set A, right? B intersect C, A union B intersect C is just this part. So the option C, we got complement C union complement D. Here by De Morgan's law, we got complement C union complement D equals complement C intersects D. So, and what the complement of C intersect D, just the universe minus C intersect D. So here the minus sign means difference. So we have to calculate the difference between the universe and C intersect D. So here we have a universe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We also have the C here 1, 2, 3, 4, 5, 7. Right, 1, 2. 1, 2, 3, 5, 7. No 4 here. 1, 2, 3, 5, 7. We also have the 2, 4, 6, 8 here is D. And the intersection of C and D is just 2, because 2 is only common part. And then we calculate the difference between the universe and a set which has only 2 as element. Then we got 1, 3, 4, 5, 6, 7, 8, 9, 10. So here is a Venn diagram. So the Venn diagram is this part is I label it as 2. So universe minus the 2 is just the other in the universe. So we have everything in universe except the element 2. So the next one is complement of C intersect D. So it is same as the operation C, because we have by De Morgan's law complement C union complement D equals to complement C intersect D. So everything should be the same. Everything should be the same as this one. So the next one, we have A union B and the difference with C. So we do the union first. We have 1, 2, 3, 4, and 1, 2, 4, 8. The union should be 1, 2, 3, 4, 5, 8. Right? 1, 2, 3, 4, 5, 8. Yep. And after that, we calculate the difference between the A union B and C. We have C is 1, 2, 3, 5, 7. And so the difference between 1, 2, 3, 4, 5, 8 and 1, 2, 3, 5, 7 is just 4 and 8. So here A union B should be this part. A union B, and here is C. So A union B minus C, or say the A union B difference with C is this part. So this is a Venn diagram of the operation E. What we have in F. So we ask to calculate A union B in difference with C. So it's just we do the difference first. Here we have 1, 2, 4, 8 is B and 1, 2, 3, 5, 7 is C. So the difference between the 1, 2, 4, 8 and 1, 2, 3, 5, 7 is 4 and 8. Right? Because the difference means the element in A but not in B. So what do we have here? We have 1, 2, 4, 8 in A and 1, 2, 3, 5, 7 in B. We have 4 and 8 in A but not in B. So here we have, obviously B and C in this question. So it's just, so 4, 8, 4, 8 is a subset of B but not a subset of C. So we got 4 and 8 here. Then we do the union. So 1, 2, 3, 4, 5 union 4 and 8. We got 1, 2, 3, 4, 5, 8. So in Venn diagram, B minus C. So here's B. The part C. Here's part C. So if we do the B minus C, we got this part. Then we do the union. We have A here, this one, union this part. We got this whole part. So we have 1, 2, 3, 4, 5, 8. In operation G, it asks you to do B minus C minus D. It's just so we have to calculate the difference between B and C first, then do the set with the then calculate the difference between the set and the D. So here we have B, C. So the difference between B and C is 4, 8, like the last question. And after that, we have 4, 8. Then we do the difference between the 4, 8 and the 2, 4, 6, 8. It's the empty side, right? Because we don't have an element in A but not in B. So by definition, A minus B, or say the difference between A and B, is just x belongs to A and x not belongs to B. We don't have any element belongs to A but not belongs to B. So we have this Venn diagram. We don't have anything colored with yellow because the final result is empty side. Here we got the common part is 2 for both the B, C, and D. And we have 1 and we have 1 and 4, 8 in B here, and we got the 3, 5, 7 in C. We also have 6 in D, and result it should be empty set. In H, here is B minus C minus D. We do the difference between C and D first. So we have 1, 2, 3, 5, 7, and it's C, and 2, 4, 8, 7, 2, 4, 6, 8 is D. So the difference should be 1, 3, 5, 7. Because 1, 3, 5, 7 is in set C but not in set D. So after that, we should do the difference between B and the this set. So we got 2, 8, 2, 4, 8, 2, 4, 8, 3 elements. So what's the Venn diagram? Here's Venn diagram. And the Venn diagram shows that we got 2, 4, 8. So C minus D, here is C, and here is D. So C minus D, actually this part. And then we do the B minus C minus D. So, oh sorry, C minus D, actually this part. Sorry about that. This part is label it as C minus D, and then we do the B minus C minus D. Here is B, and here is C minus D, so we got this part. It's 2, 4, 8. The last one, we have 1 union B minus C intersect D. So we calculate the union first and calculate the intersect second. Then the last step is do the difference between the A union B and C intersect D. So what we have in the A union B, we got 1, 2, 3, 4, 5, 1, 2, 4, 8. So we have 1, 2, 3, 4, 5, 8 here. Then what's in the intersection? We got 2 is the only common part. So here's 2. Then we do the difference. We have 1, 3, 4, 5, 8. Here is the Venn diagram. A union B is this part. Here's the A union B. So it subtracts this part from the unit set. And where is the C intersect D? Here's C, and here's D. So the only common part is here. So as we showed in the above operations, here is just 2 actually. So 2, so 1, 2, 3, 4, 5, 8. Subtract the element 2. We got 1, 3, 4, 5, 8. And this is Venn diagram. In question 3, it asks you to demonstrate each of the following using Venn diagram. Assume a universe U. So in first question, we got if A is a subset of B and C is a subset of D, then A intersect C is a subset of B intersect D, and A union C is a subset of B union D. Okay, so firstly we draw the set A and B. So here is B, here is C, and C is a subset of B. And then we draw the sets D and set C. So C is a subset of D. Then we can conclude that A intersect C, this part, is a subset of B intersect of D. So here we have this part is B intersects of D. Right. So this whole part is B intersect of D, and this part is A intersect of C. So then the A intersect of C is a subset of B intersect of D. This one is true, right? So this part is okay. Then the second part, A union C is a subset of B union D. And what we have here, A union C is this part, and B union D we got here, B union D. Here's B union D, everything here. And A union C is a subset of B union D. So this part is also true. So the second one, the option B, statement B, it asks you A is a subset of B if and only if A intersect complement B is a empty set. So how can we represent this statement by the Venn diagram? So here is a Venn diagram. A is a subset of B. So we have A is a subset of B if and only if A intersect complement B is empty set. So this part is a complement B. So we have what we have here is A intersect complement of B is empty set. Is that true? Right. So and if we have A intersect complement B is empty set, then this one is the subset of B. So we prove the forward implication and then backward implication. So the statement C, we got A is a subset of set B if and only if A complement of A union set B is the universe. So A is the subset of B if and only if A complement here is complement of A, everything except A union B. Here is B is a universe, right? Yeah, it's true. and if the A complement Union B Union B here is a universe, then A is a subset of B. This is true. So we demonstrate all of the statements by the Venn diagram. Question 4 asks you to prove or disprove each of the following statements. So let's have a look at the statement A. What do we have here? As it says, for sets A, B, and C, all of the three are subset of U. If A union C equals B union C, then A equals to B. We want to disprove this statement, but in order to disprove this statement, we can raise a counterexample. So let U equals to 1, 2, 3, A equals to 1, and B equals to 2, and C equals to 1, 2. All our assumptions are set. Yeah, we U is universe with element 1 to 3, and A is element with element A is a set of element 1, and so on and so on. So what do we have here? We have A union C equals to 1, 2, and B union C equals to what we have? We have 1, 2. So A union C equals to B union C, but A is not equals to B, because we have A is 1 and B is 2. So next one, it has 4 states ABC. ABC, all of the ABC are subset of U. If A union C equals B union C, and A intersect C equals B intersect C, then A equals to B. So we prove this statement by contradiction. Assume A is not equal to B. Without loose generality, so the WLOG means without loose of generality. So we see that there exists X belongs to A and X is not belongs to B. So then we have X belongs to A union C. And we know that A union C equals B union C, right? So X equals X belongs to A union C implies or means X belongs to B union C, and then we got X belongs to C since X is not belongs to B. So, but what we have here, we have X belongs to A, X belongs to C, X belongs to A intersect C, X belongs to C, X not belongs to B, means X is not belongs to B and C. But the statement says that A intersect C equals B intersect C. So here is a contradiction to our premise. So contradiction found here. We have X belongs to A and C, X not belongs to B and C, but the premise A intersect C equals intersect C equals B intersect C. So here is a contradiction, which means our assumption is false. So we got A equals B. Yeah, then we done our improvement. In question 5, it asks you to prove that the difference between A and B equals to A intersect complement of B. So to show the difference between A and B equals to A intersect complement of B, we have to show that for any set AB, we have A minus B, or say the difference between A and B is a subset of A intersects B, and we have to show that and A intersect complement B is a subset of A minus B. So we do the forward implication first. So we show the first we show A minus B is a subset of A intersect B. A intersect the complement B. So that X belongs to A minus B. We got X belongs to A, and X not belongs to B, right? It's by definition of difference. After that, we have X not belongs to B, so we know X belongs to complement of B. It's by definition of complementary. Thirdly, we have X belongs to A intersects complement of B, because we have here. It's by definition of intersection. So we done the first step. Second step here, we show A intersect complement of B is a subset of A minus B. So let X belongs to A intersects B. We have X belongs to A and X not belongs to B, right? So we got X not belongs to B by definition of complementary. X belongs, then we have X belongs to A, X not belongs to B, which means X belongs to A minus B by definition of difference. Here we go. We prove the difference between A and B is a subset of A intersects complement of B, and then prove the A intersects complement of B is a subset of A minus B. Then we prove the statement the difference between A and B equals to A intersect complement of B. Question 6 asks you to prove that the symmetric difference between A and B equals to complement of A intersects B union A intersect complement of B. So by definition, we have the symmetric difference of A and B. It's just X belongs to A, X or X belongs to B. It's same as the exclusive OR in propositional logic. So let's have a look at the Venn diagram. The exclusive OR means the element or the set contains the elements that are either in B or in A, but not in both. So here, this part is the symmetric difference of A and B. This part is, we should subtract this part from the A union B. And this part actually is just A intersect B. So from this Venn diagram, we can conclude that the symmetric difference of A and B is actually the A union B implies, minus A intersects B. So it means the difference between A union B and the A intersect B. So after that, if we subtract the A intersect B from A union B, it's same as we intersect the A union B with the complement of A intersect B. So what we have A intersect B here. So the complement of A and A intersect B is this part. So except the A intersect B is the complement of A intersect B. So the A union B minus A intersect B is just actually the A union B intersect the complement of A intersect B. So we can change this representation to A union B intersect complement of A intersect B. Yep. So by Demarcus law, we have A complement of A union complement of B. After that, apply the distributive law. We have A union B intersect A union B intersect of complement of B. So apply the distributive law again. We got the A intersect complement of A union B intersect complement of A union union here A union A intersect of B union B intersect of complement of B. So this part will be true. This part will be false, and this part will be false. Then we have B intersect of A union A intersect of B. And what's our conclusion? So then we got complement of A intersect B union A intersect complement of B. Right, then we done our proof. The operations in set theory is very similar to the one that we have learned in propositional logic. We do have something like identity law, the commutative law, the associative, distributive, and so on and so on. And when you ask to prove or verify or do some operation in set theory, you can apply the logic from propositional logic into the set theory. It's very similar. And yep, I think that's all the content of this tutorial. Thank you.